is the binary shift keying techniques using coherent deduction. Where coherent deduction is nothing but we are using local carrier is in the transmitter side as well as we are using in the receiver side also. That is the same carrier is used in the receiver to get back the original signal. So consider this is a phase shifting. Phase shift keying means nothing but we have a phase shift of from 0 to 1 or 1 to 0. We have a phase shift, that is we are considering only two bits, that is 1 and 0. So in a binary PSK system, the pair of a signals S1 of t and S2 of t are used to represent a binary symbols 1 and 0 respectively. That is, for symbol 1 we can call it as an S1 of t is equals to square root of 2 EB by TB cos 2 by FC of t, where the time duration t varies between 0 to TB. And for a symbol 0 we consider the S2 of t is equals to square root of 2 EB by TB cos 2 by FC of t plus pi, because we are doing the phase shift. So this equation can also be written as square minus of square root 2 EB by TB cos 2 by FC of t. Duration is 0 to TB only, where TB considered this TB is considered as a bit duration and dB is considered as a transmitted energy signal energy per bit. And consider here in the case of PSK, there is only one basic function of a unit energy, because we are using only one basic function. Look at this, is just a block of a bpsk signal, that is the input is a binary sequence. We are multiplying with the binary signals with phi 1 of t. Here phi 1 of t is nothing but I told it's a basic function of a unit energy. This phi of t can be written as 2 square root of 2 TB by cos 2 pi FC of t. That is we are for symbol 1, binary symbol 1, we are using square plus square root of EB, and binary 0 we are using square root of minus EB. And if we multiply binary signals with phi 1 of t, we will get a bpsk signal. Therefore the transmitted signals are given, that is an S1 of t is equals to square root of EB into phi 1 of t. That is, compare this equation with this equation. Comparing this S1 of t equation with this equation, that is, look at this both, we can return as an, that because we know that phi of t is equals to 2 by TB cos 2 by FC of t, where this is look at this, comparing to this EB, this is similar like in phi of t only. So we can write it as a square root of EB, that here in the remaining term is only EB. So square root of EB into phi 1 of t. And for a symbol S2, that is for a symbol 0, we will use minus square root of EB by EB into phi 1 of t, where the duration is varies between 0 to TB only. This is for symbol 1 and this is for symbol 0. Next, look at the signal space diagram for an bpsk signals. So we know that there is only one basic function, that is called as a unit energy. Phi 1 of t is equals to square root of 2 EB by TB cos 2 by FC of t, where S1 of t is equals to square root of EB phi 1 of t, and S2 of t is equals to minus square root of EB phi 1 of t only. And because we have only using the one, we are using only one basic function of a unit energy. This BPSK system is characterized by a set of antipodal signal. Antipodal signal is nothing but a pair of sinusoidal waves that differ only in the relative phase shift of 180 degree. That is, from phase shift 0 to 1, from 0 to 1 or 1 to 0 phase shift, that signal we can call it as an antipodal signal, that can be represented in only one dimensional signal space. The one dimension is nothing but an n is equals to 1, which signal constellation consists of an here two message signals, that is M1 and M2. The coordinates of two message we can call it as an S11, that is 11 is equals to square root of 0 to tb S1 of t phi 1 of t into dt, because it's an S1 means this is 1, that is the symbol 1, and this is the correlation of symbol phi 1 of t. We can write it as a plus of square root of EB. And next is the S2 of t. It also varies from the binary bit duration integral of 0 to tb S2 of t into phi 2 of t, S2 of t into phi 1 of t, S2 of t into phi 1 of t into dt is equals to minus square root of EB. Consider this is an signal space diagram. Here this is a decision boundary. We, as I told, we have a two message signals, that is the message, this one, this is at this point S1, we can call it as a message point M1, and this we can call it as an S2, that is message point 2. We can message point value is the square root of EB, and point 2 we have a minus square root of EB. The values S1 is in lies between the region Z1, and S2 lies between the region Z2 only. This is the decision boundary we told. Okay, next going for an generation of a binary PSK. Here in the generation of a binary PSK, that is the generation of binary PSK using coherent detection. Detection will not come for the generation only. Okay, next binary data sequence. Here in the binary data sequence, look at, this is a block diagram. For binary data sequence, we are using the polar non-return to 0 level encoder, and we'll multiply with the product modulator. That is in the product modulator we are multiplying the binary data, that is an NRZ encoded values are multiplied with the normal unit function, that is phi 1 of t, and we will get at the receiver we will get the more binary PSK signal, that is the transmitter and the receiver. We can call it as a transmitter as well as the generation also. Generator consists of in two components. The basic thing is the two components, that is the polar NRZ level encoder, that is non-return to 0 encoder, and next is the product modulator, where in the polar NRZ modulator, which represents the symbol that is 0 and 1 in the incoming of the binary sequence by amplitude levels of plus square root EB and minus square root EB respectively. That is, it just represents the, that is for symbol 1 we will have an amplitude EB plus square root of EB, and for a symbol 0 we will have an amplitude of an minus EB, like that. Then for this signal 1 and 0 are multiplied with the product modulator, multiplying in product modulator with phi 1 of t, here which multiplies the output of an polar NRZ encoded by the basics function phi 1 of t. The sinusoidal phi 1 of t acts as an here the carrier at the binary signal, and we will get the bpsk signal, that is S of t. But next is the coherent binary PSK receiver. Yes, coherent binary PSK receiver, as I told in the starting only, that is for a coherent detection we are using the carrier signal, that is whatever we are used in the transmitter side, same carrier we are using the receiver only, receiving side also. Consider this is an bpsk signal x of t. These signal are multiplied with the phi 1 of t, that is in the correlator. In the receiver side, consider that we have a two important components, that is the correlator as well as in the decision device. Where in the consider the basic components there are two basic components in the binary PSK receiver, that is the correlator as well as in the decision device. Here the correlator correlates the received signal x of t receives the x of t signal with the basics function phi 1 of t on a bit by bit basis. It is the bit by bit basis, that is x of t will get an either 1 0 or 0, there is a continuous signal only, multiplies with the phi 1 of t and integrates the signal, and we'll get an x1 of t, where and the decision device at a threshold value 0, at threshold is equals to 0, the decision device decides that's the whether the binary bit the symbol is 1 as well as the 0. That is, if the threshold value is 0, if choose how when it will be symbol 1 is nothing but if x1 of 0 is greater than x of 1 is greater than 0 means the symbol we can call it as in 1, and when x of 1 is less than 0 means we can call it as a symbol, we can represent as a symbol 0 only. And next is the error probability of basics for bpsk coherent detection. As I told in the disease signal space constellation diagram, that is for a symbol message signal 1, we will have an it as a region, we will get in the region of z1 only. For a message signal s2, we will have a symbol of a region of a z2 only region. Here we partition the signal space diagram into two regions, that is the set of points closest to the message point at 1, message point 1 at plus square root dB, and the set of points closest to the message point at minus square root of EB, that is we partition which is the nearest. Then the decision regions are marked as an here z1 and z2 are the decision regions are marked according to the message around which they are constructed. This is the decision rule is now simply to decide that the signal S1 of t was transmitted, that is the S1 of t signal was transmitted, that is the signal S1 of t is transmitted at the receiver side, the signal points falls in the region of a z1 only, then the output symbol we can call it as a 1, and if the binary bit symbol 0 is transmitted means the signal s2 was transmitted in the s2 side. If the received signal points falls in the region z2, then the output we can call it as a symbol 0 here. And there are two kinds of erroneous decisions occur if that is how is nothing but if signal s2 is transmitted but the noise such that the received signal should the received signal point falls inside the z1, we are transmitting the signal s2, that is symbol 0, but the receiver side but the noise such that it falls in the region z1, so that the receiver decides the flavor of it is a signal s1 only, like that. And for next is the S1 is transmitted signal, but the receiver noise is such that the receiver or signal point falls inside the region Z2, so that the so that the receiver decides in favor of a signal S1 S2. Here we are transmitting S1, but the decision device decides whether it's a flavor received signal may be S2 due to noise error. And consider the decision region associated with symbol 1 or the symbol signal S1 of t is described as an Z1 is to ratio, that is x1 lies between the 0 to infinity. Here the symbol 1 region Z1, so the values x1 values varies between 0 to infinity. The observable element x is related to the received signal x of t. We can draw it as an x of t is equal to 0 to tb x of t into phi 1 of t into dt. This is the correlated output signal. And the conditional probability density of a function random variable x1 given that the symbol 0, the s2 was transmitted. So we can write it as a function of an, that is f of x1 into, that is in the bracket, x1 of by 0 is equals to 1 by square root of pi n naught exponential of minus 1 by n naught into x1 minus s21 whole square. This is a standard equation, that is the conditional probability density function, that is 1 by square root of pi n naught, and this is an exponential term of an, that is the x1 into the for a symbol 0, or what I told is an s to 1 only, so we need to square that one. So we can write it as an s to 1 as an plus square root of EB, because as I told in the starting only here, here, that is s2 of t is equals to minus square root of EB. So we can write it as an s2 of t is minus into minus is the plus, so we can write it as a plus square root of EB, or we can write it as an here also. Look at it. So next is the conditional probability of a receiver decides in the weather of a symbol flavor of a symbol 1, given that the symbol 0 was transmitted. Consider this is a symbol 0 was transmitted, but in the receiver deciding it's a flavor of a 1, that is 0 was transmitted, but the receiver will receive the symbol as a 1. It decides, okay. We can write it as a 1 by pi, so that is 1 by square root of pi n naught into integral varies between 0 to infinity exponential into this term, that is minus 1 by n naught into x1 plus square root of EB whole square into, that is the differential with respect to the dx1. Then consider this is a, this we can write it as a z is equals to 2 n naught into x1 plus EB square root of EB, where we differentiate with respect to z is nothing but dz is equals to square root of 2 n naught into differential of an x1 dx1. And next is the, consider when x1 is equals to 0, here when x1 is equals to 0, consider here the x1 is equals to 0, then the value of the z is equals to here the value of the z is equals to 2 by n naught into EB, 2 by n naught into EB, that is if we differentiate, that is dz means integral of the square root of 2 n naught, 2 by n naught into EB, and x1 when x1 is equals to infinity, here with respect to x we are differentiating, no? So when x is equals to 0, the value z is equals to square root of 2 by n naught into EB. When x1 is equals to infinity, then z also turns to infinity, because if we multiply the signal with an infinity, we will get an answer only infinity. So this can be written in the above equations, that is 1 by square root of pi n naught into integral varies from here, when the integrals varies here it changes, 0 means it changes from square root of 2 EB by n naught into integral varies from z to z only, then exponential term of an minus z square by 2 into square root of n naught by 2z. Here we can how we can written is nothing but there, this is just this value, and p of 10 is equals to, here this n naught get cancelled, that is square root of n naught into square root of this n naught, and the remaining term is nothing but an 1 by multiply the here in the multiplication, this n naught, this square root of n naught and this square root n naught get cancelled, n naught n naught, so the remaining term is square root of 2. So we can written as 1 by square root of 2 pi. Integral varies between same duration only, that is 0 to square root of 2 eb by n naught into integral exponential term. Here this term we are already, that is n naught get cancels, only 2 is there, this we are multiplying here, that's outside the integral. So remaining term is exponential of minus z square by 2. That is we have a formula, that is a q function, we can call it as a 1 by square root of 2 pi. Integral varies from x to infinity, exponential into minus t square by 2 dt. Here the Gaussian random variable x, here x is nothing but a Gaussian random variable. So we get p10 is equals to, by looking to the above equation, we can write it as in q is equals to square root of 2 eb by n naught, eb by n naught. This is the probability. So consider next an error of a second kind. Here the error is a first kind, that is the symbol 0 was transmitted, but at the receiver it receives 1. So next is the conditional probability of a receiver decides the whether of a symbol 0 given that the symbol 1 was transmitted here. So comparing to this, this can be already written as a, that is same only, it is same steps we need to follow. We will get an probability p01 is equals to q into square root of 2 eb by n naught, 2 eb by n naught, and the average probability of a symbol we can call it written as a pe is equals to p0 into p10 plus p1 into p01. That is, we can call it as an, this is a probability is nothing but in 1. So 1 it is divided by 1, this one is 1 by 2 plus 1 by 2 is 1 only. So we can write it as a probability, that is a 0, that if we add that the probability should be 1. This is the general concept of a probability. So 1 by 2, this is a 1 by 2 and this is 1 by 2 into q square root of 2 eb by n naught plus 1 by 2 q square root of eb by n naught, where p is equals to square root of this half and this half is 1. We will get an q 2 square root of 2 eb by n naught only. And next concept is